Welcome. When you use a really complex piece of software, it can feel, it can feel like magic. Today, we're going to peel back the layers and look at the hidden machinery that makes it all tick. We're taking a journey from the operating system all the way down to the code itself to uncover the big design choices that make everything work.
I mean, really think about it. You click an icon on your screen, and this massive, intricate application just appears. It seems so effortless, right? But underneath that seamless experience is a whole world of really tough, really clever architectural decisions. And that's exactly what we're diving into. We're going to look at 4 different layers of software. We'll start at the very bottom with the operating system, then move up to application frameworks, then the cloud, and finally, the programming language itself. And what you'll see is that at each layer, a totally different problem requires a totally different and sometimes radical solution. Okay, so let's start at the absolute foundation, the operating system. Now, what if you wanted to build something for maximum, blistering speed? What if you just stripped away everything that wasn't 100% essential? Well, that's the wild idea behind our first concept, the unikernel.
Think about it this way. A normal OS is like a giant toolbox, right? It's got every single tool you could possibly imagine just in case you need it. A unikernel, on the other hand, is like a custom-made tool, built to do exactly one job and do it perfectly. It takes your app, grabs only the operating system libraries it absolutely needs, and compiles them all into one single super lean file.
And the difference in philosophy here is just fascinating. On one hand, you've got your traditional OS, built for flexibility, ready for anything. But on the other, you have the unikernel. It actually gets rid of the separation between the app and the OS core. It's like tearing down the walls inside a house. This makes it incredibly minimal, which is great for security and, as you're about to see, absolutely incredible for performance. And the numbers, well, they're just staggering. A standard Linux virtual machine takes up 1.6 gigabytes of space. A much more efficient Docker container still comes in at 117 megabytes. But the Zephyr unikernel, get this, a mere 70 kilobytes. That's not just a little smaller, that's an entirely different universe. It is literally the difference between a novel and a tweet. And it's the same story with memory usage. The VM needs 78 megabytes, Docker 5.6. The unikernel just sips a little over 1.5 megs of RAM. This isn't just about making things a bit faster. This is what makes it possible to run software on tiny little IoT devices and sensors where every single byte counts. And here it is, the knockout punch. Startup time. Over 10 seconds for the virtual machine to get going, a third of a second for Docker, which is pretty fast. But the unikernel, 1/10 of a second. It's practically instant. This makes it perfect for situations where you need to spin services up and down on a dime. So let's just let that sink in for a second. We are talking about a 98% reduction in RAM usage compared to a full virtual machine. That is just a massive, massive gain in efficiency. And it's all thanks to one single architectural choice. So the takeaway here is really simple. The core design philosophy is minimalism. By throwing out everything that isn't absolutely critical, you get a much smaller attack surface for security, and you get these incredible leaps in performance. The trade-off, of course, is that you lose flexibility. This isn't for your everyday desktop computer. It's for doing one thing and doing it extremely well. Okay, so let's climb up a layer. We're moving from the OS itself to a really complex application that runs right on top of it, Anaconda. This is the installer for big operating systems like Red Hat Enterprise Linux. And here, you'll see the design goals are completely different. Anaconda has to juggle this really complex, multi-stage process. It's got to partition your hard drive, install all the software packages, set up the bootloaders so the system can even start, and then configure the whole thing. This is not a simple task. It's a complicated workflow with a ton of moving parts. So how in the world do you manage all that complexity? Well, Anaconda uses this really clever hub-and-spoke model. There's one central summary screen. That's the hub. And every individual task, like setting the time zone or configuring the network, is a spoke. The cool part is you can jump between these spokes in any order you want, which gives you, the user, a ton of flexibility. It also means it's super easy to add new features later on by just adding a new spoke. And this brings us to our next big principle, modularity. See, unlike the unikernel, which wins by eliminating complexity, Anaconda wins by taming it. It breaks a huge, messy problem down into small, independent, and totally manageable pieces. All right, let's zoom out even further. Now we're going big. We're scaling up to the cloud and looking at OpenStack. This is a massive open-source platform for building and managing your own cloud infrastructure. And believe me, this is complexity on a whole other level. You know, as one OpenStack contributor put it, a real cloud isn't just about firing up virtual machines. It's this entire ecosystem of different services. You need networking, you need storage, you need databases, you need messaging systems. The list just goes on and on. And that's exactly where OpenStack's big tent philosophy comes into play. See, it's not one giant monolithic piece of software. It's actually a collection of tons of independent projects that all know how to talk to each other. You've got Trove for your databases, Magnum for containers, Glance for machine images. Each one is a service in its own right. So, the key principle for cloud platforms like OpenStack is composition. You build an incredibly powerful system not by trying to write one giant program that does everything, but by composing it from smaller, specialized services that all work together, kind of like building with Legos. Now, for our final layer, we are going right to the heart of it all, the programming language itself. And specifically, we're going to look at a really fundamental architectural choice in the Python language that has shaped how it works for decades. We're talking about the infamous Global Interpreter Lock, or the GIL. The best way to think about it is like a single microphone in a room full of people. Even if you have tons of people, or in this case CPU cores, ready to talk, only one person can hold the microphone and speak at a time. Now, this made things a lot simpler back in the early days of Python, but with today's multi-core processors, it has become a major bottleneck. And look, this isn't just some academic debate. This quote comes from the DOSE 3D project, which works on cancer radiotherapy, so pretty high stakes. They found they were spending more time just shuffling data around than actually processing it. When they switched to a version of Python without the GIL, the results were, in their own words, astonishing. This real-world impact has led to a huge proposal to make the GIL optional in Python. But this isn't some small tweak. We're talking about a fundamental seismic shift. Getting rid of that single microphone requires a complete re-architecture of Python's core, especially around how it handles memory and makes sure different threads don't step on each other's toes. That's what we call thread safety. But, you know, there's no such thing as a free lunch. All these new safety mechanisms add a little bit of overhead, so single-threaded programs might actually run a few percent slower. So why on earth would you do it? Well, because the payoff is that for the right kind of problem, multi-threaded code can finally run wild across all of your CPU cores, unlocking huge performance gains that were just impossible before. So what a journey, right? We've traveled through 4 really different layers of software, from the bare metal OS all the way to the language interpreter itself. Let's take a step back and see what this all means when we tie it together. At each and every layer, we saw a different architectural principle win the day, each one a brilliant solution to a very different kind of problem. We saw minimalism for raw, unadulterated performance. We saw modularity for taming complex workflows. We saw composition for building massive, scalable platforms. And we saw re-architecture for evolving a language to meet the demands of modern hardware. What this really shows us is that software engineering is a story of trade-offs. There's rarely a single right answer, and it leaves us with one last big question to think about. The GL was a rule that made sense for decades, but now it's being broken to fit the reality of multi-core processors. As our hardware continues to change in wild and unpredictable ways, what fundamental software assumption do you think will be the next to fall?